by Andrey Varlamov. Good afternoon, everybody. I want to thank organizers for this kind of invitation, and I was asked to deliver 2 lectures about the fluctuation phenomena in superconductors. And the plan of my lecture is the following. First, I want to approach the problem in 3 touches. First one, qualitative, to describe the problem and to evaluate the answers by the hand waving. The second, based on phenomenal time on the Ginzburg-Landau phenomenon. And the third, just to give you the ideas of microscopic description. And then finally to finish with the modern results of fluctuoscopy, when study of fluctuations is not mainly fundamental problem, but became a tool to extract microscopic characteristics of modern superconductors. So this is what I would like to do in these 3 hours. And the first lecture today will start from description, qualitative, from Rayleigh Jeans waves to Abrikosov clusters, qualitative of fluctuations in superconductor. Then to put in front the finding of Kamerlingh-Onnes as a contradiction to the famous statement of the Gottfried Leibniz. Then I want to pass to discussion of fluctuations based on simple Heisenberg principle. To extract from the Heisenberg inequality, I want to extract the lifetime of Cooper pairs. And based on the Einstein-Smoluchowski diffusion law to find their lengths. Then I want to answer on the question how many fluctuation pairs are about, how their presence changes BCS critical temperature. Then what is the physics of the main fluctuation events? Then I want to pass in the phase diagram from the closeness to TC in the zero magnetic field to the quantum phase transition at 0 temperature at HC2. Then I don't know, maybe this is too trivial, but I want before to study the how fluctuations can be described by the Ginzburg-Landau functional. So beyond because you understand that Ginzburg-Landau equations are the minimal point of Ginzburg-Landau function. So a saddle point. So I want to recall just the derivation of Ginzburg-Landau equations and relate it with this some delicate points like a normalization, what is the mass of Cooper pair, etc. So maybe here I will be trivial, but you will allow this. And at this moment, then maybe I will say several words about the achievements of Ginzburg-Landau theory, its achievements of 1950, so that Ginzburg-Landau theory had succeeded to explain the fundamental problems of superconductivity of those times, and then the application of Ginzburg-Landau theory where Ginzburg and Landau did not expect it. Moreover, Abrikosov found vertex solution, and Landau 3 years did not allow to Abrikosov to publish. So I will start from so this is the just visualization what I would like to discuss today, and let's start from 1704, the new essays of Gottfried Leibniz, who stated that natura non facit saltus, natura does not make jumps. And I want immediately to show you the famous dependence of critical of the resistance of very narrow, thin mercury wire, which demonstrated just opposite to statement of Leibniz. You have here beautiful jump. And I want to recall you that just this jump was not expected at all, because this measurement happened because since 1900, when Drude proposed his formula for the conductivity of normal metal, which we still use, in spite of it was written in classical imagination, it still works. But then was a beautiful dispute between Drude Lorentz and Kamerlingh-Onnes from one side and Lord Kelvin from other side, because Drude told, and Lorentz confirmed it, that at zero temperature, electrons should, so the motion is, so they believed that relaxation time, due to the stop of thermal motion, relaxation time becomes infinite. So from Drude formula, conductivity should be infinite and resistance zero. Lord Kelvin, vice versa, he believed that at zero temperature, electrons must be localized around their ions in metal. So you will not have free carriers. So there was two versions. One, that resistance goes to zero. Another, it goes to infinity. The question was about the, so the person who could answer this question was the only. It was Kamerlingh-Onnes. Because until 1908, liquid helium did not exist. It was Kamerlingh-Onnes who liquefied helium in July of 1908. Before, many people tried to understand what is the temperature dependence of the resistance of metals. It was Cailletet, the French academician, who had succeeded to liquefy oxygen. It was Wróblewski, who was Polish scientist who learned from Cailletet and bought equipment, and he had succeeded first liquefy liquid helium, not only like small drops, but in large quantities. It was Dewar, but Dewar arrived to liquid hydrogen temperature. He was the first for liquid. So it was the only person, Kamerlingh-Onnes, who tried to liquefy, who liquefied helium and started to put the point in this discussion about the low temperature behavior of resistance of metals. And he expected that actually the resistance will go smoothly to zero. He did not believe in increase according to Lord Kelvin, and he allowed actually the article about the growth of resistance was published in Proceedings of Laboratory of Leiden Laboratory. So in spite that Kamerlingh-Onnes did not believe in this, he allowed to publish this article. So, but what Kamerlingh-Onnes measured always was some finite value. It is why he chose the mercury, because mercury was easy to clean at room temperature where it was the liquid. And he found this jump. So it contradicted, it was absolutely unexplainable. It was impossible to explain in the background of classical physics. It was unexpected. And people usually identify this picture with the 8th of April of 1911. This is not true. This picture this graph was obtained in the October of 1911, much more precise. The first measurements of chameleon honest were not so precise. Here he guaranteed almost 400 times measurements, etc. So actually here he moved not from above to below, but vice versa, from low temperatures to high temperatures. Okay, so this is Christoph recognized very good this feature, I suppose. So these are modern measurements of superconducting transition in thin titanium nitride films. And you see that we return again to the ideas of Leibniz. Here, impossible to say where is temperature, where is critical temperature. And these curves behave, they grow before to go to zero. And so it is interesting to understand why it is so, how this transition happens. And here we help fluctuations. So let's start from the basic principles of quantum mechanics. So I'm in normal metal, I reduce temperature, I approach TC. What happens when temperature reaches TC? It becomes energetically profitable to create Cooper pairs. And then simultaneously in BCS picture, they will start to condense and you will have a coexistence of quasi-particles. So the electrons slightly will change their spectrum. The gap will appear, but it is small, and condensate of Cooper pairs. But why do not try to create Cooper pair above this? It is possible, but it is energetically not profitable. But nevertheless, in accordance to Heisenberg principle, I can evaluate the characteristic time of such coexisting together. So this is not a marriage. This is a temporal trying to live together. So what I have, Heisenberg tells us that the uncertainty in time is h bar divided uncertainty in energy. So if I want to know how long such Cooper pair, such pair of two electrons will coexist together, so I have to put in the denominator some corresponding energy. What energy I can put? What I have? Fermi energy, omega d by Tc, T, nothing. Fermi energy have nothing in common with bosons. The omega d bar already, it is phononic energy and it is included in Tc. Moreover, I know that Cooper pairs, I just will change temperature for 1 millikelvin and I will be in superconducting state where they are eternal. So my characteristic lifetime of Cooper pairs must be divergent at the point Tc. So I will write that energy which is in the denominator is just T minus Tc. Immediately, many people can take stones and throw it to me. They can say, why in the first power? Why in the first power? The answer will be more or less like Landau in his theory of phase transitions. He taught us that the coefficient in his free energy is proportional to T minus Tc. So the motivation is the same. And it works. And then now you understand that it is easy. It is easy to construct such qualitative discussion when you already have results of microscopic theory. So this corresponds to microscopic theory. And indeed, if I will put the T minus Tc in denominator, so the lifetime of Cooper pairs, which is called Ginzburg-Landau time, so it will be expressed in reduced temperature, epsilon T minus Tc, it is log T over Tc, but I work close to Tc, so this is T minus Tc over Tc, which is supposed to be much less than 1. In microscopic theory, we can cover everything, but here it is much less than 1. And for future, I will write this Ginzburg-Landau time in some strange form. I will say that this is h bar Boltzmann constant minus 1 Tc minus 1 epsilon. You will see why I write this. So it has T minus Tc in the numerator. Now, so I established that if such pairs exist, spin up, spin down, or they live together time 1 over T minus Tc, and then what size do they have? Let's suppose that for simplicity, it is possible to show all these pieces.
One very small question. Is this divergent time scale similar to critical slowing down?
This is okay. This is a theory which valid beyond critical region. So this is a simple critical index, but of course, when you enter for temperatures very close to Tc, it can change. It will depend on dimensionality, etc. Here, this simple Ginzburg-Landau. First of all, I want to determine what I will call fluctuations. I will call fluctuations all beyond mean field. So BCS is mean field, and I try to take into account the effects beyond. This will be the goal of all my 3 hours. Okay, so let's suppose that I had spin up, spin down 2 electrons in the same point, and then I left them to move in diffusion rate, so dirty system. So they will scatter by impurities, and I can evaluate the distance at which they will go away during this time as a square root of diffusion coefficient for electron multiplied just obtained Ginzburg-Landau time, and I will see if I will put here the expression for Ginzburg-Landau time. I will find that the size which I can attribute to such pair is the BCS coherence length divided square root of reduced temperature, T minus Tc. So this is Ginzburg-Landau length, and I got it just by hand wave, but of course appealing to what I know from Ginzburg-Landau. Very so now the question is how many these Cooper pairs in 1 cubic centimeter. So their concentration. I will say that I believe that they're bosons. So I would use the Bose-Einstein distribution with the 0 chemical potential, and in assumption that this energy is very small, much less than temperature, I will expand exponent, and I will get Wien distribution, well-known classical Wien distribution. Why I say that it is possible? Because I evaluate the energy of the pair as its inverse in lifetime. So they are not quasi-particles in sense of definition of Landau definition, that quasi-particle should have the relaxation time much longer than its inverse energy. So they are not, but nevertheless, the Boltzmann picture for, I mean that the correct way to describe fluctuations, and this is Ginzburg-Landau equation, phenomenology. But it is possible to show that in some conditions, namely for not very strong magnetic fields, you can get from Boltzmann, from Ginzburg-Landau equation, you can reduce it to Boltzmann equation. So you can treat Cooper pairs as quasi-particles. And it works for weak enough field when field does not break it. And it will, but nevertheless, you can take into account nonlinear effects in strong electric. I mean that you can, in this approach, describe not only direct current in weak fields, but you can describe even in not very high frequency fields, and nevertheless for strong electric fields. So you can take into account the effects when electric field breaks Cooper pairs. Why breaks? Because one electron moves in this direction, another in this. You apply electric field, one is accelerated, another decelerated. So when the distance between them due to electric field will become of the size of Cooper pair, it will be break. And even such delicate effects can be treated in a simplified Boltzmann picture. But nevertheless, here, I suppose that T minus Tc is much less than Tc. It was a condition to write the Ginzburg-Landau time. And here there is a, sorry, what happened? Yes. And this is just motion of the center of mass of. So I say that you have some gap. This is not gap, it's opposite sign. This is not negative, positive. Plus the kinetic energy of the center of mass. Then I will say that concentration in the integral of the Boltzmann of the Bose-Einstein distribution for different dimensionalities with some cutoff where the Yoke psi not be less than BCS1, and you find the expressions for n for concentration for dimensionalities 1 to 3. Funny that this answer includes the mass of Cooper pair, and we will see with you that this value, like Dejean, it is pleasure to cite Dejean in these walls. So Dejean wrote in his book that as a mass of Cooper pair, in principle, we can choose even the mass of Sun, because the mass of Cooper pair is a question of normalization of the order parameter, and this is our choice. So let's go ahead. I won't say that I promised you to calculate concentration, but this concentration I can calculate only with the accuracy up to the mass of Cooper pair. Very good. Now I want to start the discussion of the effect of fluctuations from the very simple thing, Tc. So we have Tc0, which was calculated in 1957 by Bardi and Cooper. In two-dimensional case, and here I discussed two-dimensional case, we know, so what means BCS picture? You have just what I discussed before fluctuations. So I have the Fermi picture, electrons live in their way, free electrons, non-free electrons. You include some attraction, component attraction or other, and at some point it becomes energetically favorable to create Cooper pairs. Immediately they condensate, you have boson condensate, and you have the quasi-particles, which are separated by gap from your boson system. So this is one picture. So here you have the change of the correlator of order parameter from exponential in normal metal to constant in BCS state. You have establishment of long-range order in the system, and this is mean field picture. We know, starting from the papers of Berezhinsky and Taulis-Kosterlitz from the beginning of 70s, that in two-dimensional superconductor happens something. Okay, we knew before from the paper of Hohenberg at the end of 60s. We knew that in two-dimensional systems something happened bad. Namely, if you calculate the correlator of other parameter in two-dimensional system, you see that the phase fluctuation kill you the long-range order at the large distances. So fluctuations destroy this point. And but Barton, Cooper, Schrieffer are innocent. They did not take into account population, they just wrote mean field. And you go beyond mean field. And something happened in three-dimensional case, okay. In two-dimensional case, already something happened with long range. So they studying this problem so this was a Hohenberg. But Berezinski and then Tauris and Kosterlitz, they studied two-dimensional system from another point of view. They proposed a vertex picture. So you have the without magnetic field. You can, in two-dimensional system, there is a specifics of logarithm interaction between vertices. And they studied that vertices and anti-vertices can be coupled or they can be free. And they identify the superconductivity with the phase of coupled vertex-anti-vertex pairs. While when they dissociate, you have the normal state. And in this way, you can, from the thermodynamic point of view, to compare entropy term and energy term, and you will find that exists so-called Nelson jump. So the transition in two-dimensional system from superconducting. So in superfluid density happens in jump. And this temperature is called Berezinski-Tauris-Kosterlitz temperature. Very good. So here is the Berezinski-Tauris-Kosterlitz. Here is BCS. Yuri Ovchinnikov in 1973 did the paper which was very, it provoked the very active dispute. He took into account fluctuations and even more in two-dimensional case, and he demonstrated that fluctuations increased time critical temperature. Impossible. Absolutely impossible. It was 1973. But Ovchinnikov, who unfortunately got 1 year ago died, he was fantastic mathematician. Actually, he saw all physics through mathematics. And he insisted that he is right. 13 years later, in 1986, Sasha Finkelstein got the Ovchinnikov result, but with negative sign. So he got the same 2 Ginzburg log 1 over Ginzburg, but with negative sign. And me, also with Dorian, the same year, in another paper, we got the same 2 Ginzburg log 1 over Ginzburg with negative sign. And it was the last battle in presence of Larkin. Larkin collected all of us. And finally, Ovchinnikov told that he cannot do mistake. But finally, Larkin told it to be all right. So, but nevertheless, I attribute this result to Ovchinnikov, not to me, because we just precise the sign. But so what is beautiful that Yuri Ovchinnikov got, that it is enough to take only in first approximation fluctuations, and they will reduce critical temperature for 2 Ginzburg numbers. Ginzburg number I will speak about. This is the strength of fluctuations. Multiply TC, logarithm 1 over. What is beautiful that if later people developed renormalization group, so they took into account all next orders, all correction to Ovchinnikov result was only for Ginzburg. So it is 4 much less than logarithm 1 over Ginzburg. 4 is number, log is parameter. So actually, already in first step, you get important result. And the cherry at the tort is that the difference between Berezinski-Tauris-Kosterlitz temperature and this TC0, so all difference is this 4 Ginzburg. So look as beautiful. You start from fermionic picture. You allow fermions to create perturbs. They condense. Then you take into account fluctuations beyond TCS, and you get some new TC. Or you forget about this, you start from vertex anti-vertex picture, you get point where superfluid density turns down, turns zero, and they coincide. Up to my mind, this is very beautiful. And you see the use of fluctuations because you have this matching between two completely different pictures of the world. Okay, so now what we can do good with these two things which we got. So tau, Ginzburg, Landau, and Xi. So for instance, I can reproduce results of 1968 of Aslamazov and Darkin just based on Drude formula. Drude formula says me that conductivity is a number of carriers, a concentration of carriers divided m, multiplied square, and scattering time. So scattering time to be scattered or to die is the same, because after scattering or after the death of Cooper pair, next will appear with zero momentum to the center. So here I definitely would put Ginzburg-Landau. Instead of charge, I will put 2e. But I have the ratio number or the concentration of Cooper pairs divided m. Look, it seems that I have it. I did not know what is a concentration, but I can divide this concentration over m, and I will give answer. I will get answer. It will be K Boltzmann TC, and then logarithm 1 over epsilon two-dimensional case, or C Ginzburg-Landau, etc. In two-dimensional case, answer is universal without material parameters. So I immediately divide n over m. I go here, and I will get this answer. So in two-dimensional case, I will reproduce e squared divided 16. It is exaggeration. 16 I cannot get. But e squared divided t minus tc, I got. Look, I can do the same trick with the magnetic susceptibility. Because the Cooper pairs in magnetic field, they rotate. So I can apply the Langevin formula for magnetic susceptibility of the atoms, the rotators. And again, I will have e square over c square. I will replace by 4e square c square. Then n over m, I just calculated, and I reproduce you the formula for the magnetic susceptibility, which means the feeling of superconductor that it will become the Meissner state. So it will be giant. Actually, the magnetic fluctuations are giant because you compare with Langevin or Landau or the paramagnetism. Very good. In principle, but so these results I got you by hand. In principle, I can get much more. If I would, I can get, even with Ginzburg-Landau, you will see I can, okay, I can easily get free energy and of responding to fluctuations. It will be proportional to t minus tc log 1 over epsilon in two-dimensional case. And then I can calculate a lot of beautiful things. For instance, I can calculate chemical potential of Cooper pairs. You can, no one tell me that it is zero. I had a long dispute with Kapnin and other people. Of course, chemical potential of Cooper pairs is zero, but below TC. Fluctuation Cooper pairs, they have chemical potential TC minus T. And it is possible to show from simple consideration in the Ginzburg-Landau frame. This allows me to get a lot of, I don't say about heat capacity. This is trivial. But it is possible even to explain the beautiful experiments of Ong, yes, please, and Kamran Bey. Yes, please.
May I ask a question about the conductivity we just calculated? This must be the conductivity of the fluctuating Cooper pairs.
Yes.
Is the charge transport governed by those fluctuations?
Yes, of course. A very good question. So you have the opening of new channel of charge transfer. There is an electronic charge transfer with scattering, so it is resistive. But Cooper pairs do not feel impurities because you already put impurities inside. So this is effective media for them. They move ballistically. Remember first Landau equation. The Landau assumption was that d density of current over dt is proportional to electric field. Not current, and current is proportional to vector potential if you integrate it. So the fact that in Landau equation it is derivative of current proportional to E means ballistic motion. Because if not, scattering would do current proportional, current is velocity. So velocity would be proportional to electric field. And here, acceleration. So this is, you are absolutely right. So you have additional channel of charge transfer. Very good. So, yes, please.
Can you explain how the chemical potential can be non-zero? The charge is still zero, right? And
Sorry?
Cooper pair charge is still zero.
No, Cooper pair charge is 2E.
Okay, sure. How can the chemical potential be non-zero?
Chemical potential?
Yes.
Okay, remember how chemical potential of both the system behaves as a function of temperature. You do not have condensate. So above TC, you still do not have condensate. They appear and disappear. And you just define what is chemical potential. It is dF minus dF over dN. If you know F and you know N, you can calculate this derivative. And it will just correspond to chemical potential. Imagine, you see, in BCS, the formation of Cooper pairs and their condensation coincides at the same point. But imagine that you have bosonic system just, and you decrease temperature. Density increases, and in some point you have boson condensation. If you look in the Landau fifth volume, you will see that chemical potential reaches this zero linearly. And what I say, it is more or less the same. So, but what is beautiful that the Nernst, what was a very important story in '99, Ong measured in high temperature superconductor on pseudo gap phase. They measured the huge Nernst effect, and they attributed to pseudo vertices because who deliver entropy vertices in superconductors. So it was a discussion, not only pseudo gap, but the vertices. I don't know what means vertices, but then it was your mentor, if I remember well, Kamran or not. Collaborator, yes, sorry. So Kamran with Alexander Pouret and Obin, he demonstrated that the effect not 500 times, but 2,000 times was measured in niobium silicium with critical temperature 0.38. So nothing common with high temperature superconductor. And so it was an enigma why Nernst effect is so strong. And the explanation is very simple, that it is possible to show in two lines that the Kelvin formula for thermoelectricity. So that Nernst coefficient is proportional to the derivative of chemical potential over temperature. So in normal metal, Bose system has chemical potential Fermi energy minus temperature squared divided energy Fermi. You derive and you have immediately T over epsilon Fermi. T over epsilon Fermi is 10 or 1 electron volt, and it is 10 minus 3, 10 minus 4. for Nernst, but if you have Bose system and chemical potential is very small, Tc minus T. But when you derive it, you have -1. So you immediately get 4 orders. And this explains that the Cooper pair, fluctuation Cooper pair, give you the giant effect for Nernst effect. What was measured by Ong and French. Okay, so now beyond Ginzburg, Landau, and because all what I found showed you, it is so-called paraconductivity. Paraconductivity, this is a fluctuation contribution, namely due to opening of new channel of charge transfer. So fluctuation surface. But there is something else. Yeah.
So the paraconductivity is like finite lifetime of Cooper pairs above TC, right?
Yes.
Like forming and
yes. And these Cooper pairs participate in charge transfer. They participate in diamagnetism and in heat capacity, etc. But this is not all, because simultaneously with this seminal paper of Varlamov and Larkin appeared another very enigmatic paper of Kazumi Maki. Kazumi Maki, who got very strange answer, and this answer was divergent. So he considered another Feynman diagram, calculated it, and showed that in case of, I suppose, yes, in case of dirty superconductor, I suppose only dirty, Mahit, it seems that he considered only dirty, yes, only dirty. So he got answer even larger than Varlamov-Larkin. Varlamov-Larkin got E squared divided T minus Tc. And he got E squared divided T minus Tc log 1 over T minus Tc. So even stronger by logarithm. But it was divergent. He could not explain this. Actually, this log, he cut by hands. He did not know how to deal with it. Actually, he should put infinity there. And 2 years later, Dick Thompson from UCLA he showed that. So it was again very interesting, long standing dispute how to cut this logarithm. And proposal of Dick Thompson was a little bit done on the knee. He proposed just introduce pair breaking impurities, which cut off this logarithm. So it was done by hand. It was not some self-consistent theory. Then later, there were papers of Patton and the Keller and Korenman, who demonstrated that it is possible to do more elegant self-consistently, take into account fluctuations, their effect, also nonlinear effects. But nevertheless, exist some strange contribution which should be taken into account side by side with Varlamov-Larkin.
but this time it's like interaction terms, right?
Yeah, I will tell you, they could not those time explain physics of it. We did it with Larkin. It is easy to be smart much later. So already existed the theory of weak localization, and we knew that there are corrections to conductivity that the system feels in advance when you increase concentration of impurities. The system increase the transition Anderson transition. So, and the first signs of it, there are self-intersecting trajectories. These trajectories, where electrons start, it scatters, and finally returns at the same place. And these trajectories give negative contribution to conductivity. So we have succeeded with Larkin in our book to explain the Maki-Thompson contribution as a special kind of pairing. So when one electron spin up moves clockwise, red, clockwise, anti-clockwise, along the same trajectories, and then they, in weak localization, these are non-interacting systems, only with impurities. And here, if you will switch on interaction between them due to electron phonon interaction, so you can get the Mackey-Thompson effect again by hands. So you will calculate probability of self-intersecting trajectory, multiply of effective interaction, and you will get answer of Mackey.
So is it electron phonon coupling or
For
electron
of course, we consider it as electron phonon, but important that you have some clue. Then, okay, there are some specific. I explained very simple for conductivity, but what we did with Mohit in '93, it is described formally by the same diagram, but their situation, because we discussed the 1/T1 time, so it was the scattering on the nuclear, nuclear magnetic moment, and the same diagram has to be treated as a double motion of the same electron, it pairs with itself, moving at such trajectory. Okay. Yes.
Relocalization gives you increased resistance, and you're talking about paraconductivity.
Sorry.
Relocalization increases the resistance, right?
Increased resistance.
And you're talking about paraconductivity.
No, now I speak about Mackey-Thompson.
Still, you have excess conductance.
Yes, yes. Here I have excess conductance.
So how is it related to
This is square.
What is square?
What?
No, because about Aslamazov-Larkin, no doubts.
No, but Mackey-Thompson goes in the same direction, right? It increases conductivity.
Yes, it increases conductivity.
How does it increase
It increases conductivity because I have weak localization. Why decrease? Because you make summation of amplitudes, and you have negative contribution. Here, I will think about. I cannot immediately say. I have to think about sign. I want to finish now with these fluctuation contributions, and so another effect that no one asked me where I took these electrons for Cooper pairs to form Cooper pairs. Of course, I took them from Fermi level because I cannot create. So another fluctuation effect must be the decrease of density of states at the Fermi level, and it happens for dirty superconductor in very narrow region T minus DC. Let's remember this. So the renormalization of density of states happens here. It was calculated by Marta Reddy, Abraham, and Wu in 1970, and the scale is very small, T minus DC. But this means, let's see what happened. Another fluctuation contribution will be with respect that not all electrons now are at their working places. Some of them went to work as Cooper pairs. So I can say that now negative contribution to conductivity will be lack of electrons on working places multiplied E squared tau divided. Number of lacking electrons is twice number of Cooper pairs. Number of Cooper pairs I will be calculated, and so what? And you see that I can say that the correction to conductivity due to renormalization of density of states would be twice number of Cooper pairs, E squared tau impurities, and it will be minus E squared log 1 over epsilon. So it is less, I speak about two dimension, it is less singular than paraconductivity and Mackey-Thompson. And it shows itself or far from TC, or in some special cases when Aslamazov-Larkin and Mackey-Thompson are suppressed. For instance, for the transversal transport in layered superconductors. So in this case, what is interesting, this effect not increase conductivity, it increases resistance. So you will have growth of resistance when you approach TC, and then you will have Aslamazov-Larkin will win because it is suppressed by transparency. But as a temperature dependence is much more simple. So you have logarithm against 1 over T minus TC squared. But T minus TC squared is suppressed by another transparency coefficient. So you can explain this we did with D. Clem and with Buzdin and Livanov in 93. No, first we showed this actually with Larkin and Yoffe and Yulu in 92. And this can explain you the non-monotonous behavior of the resistance as a function of temperature at the age of transition. Okay, so now I'm still alive. Can I continue? Now, yes, please.
I just have a question about just before when you said that the conductivity now is reduced because some of the electrons went to Cooper pairs.
Yes.
But these pairs are like also participating in the conducting processes. So
look, you have Drude. Okay, Drude means full concentration of electrons divided m e squared tau. Then you say, besides this, I have new channel due to formation of fluctuation, and it will give positive contribution. Then I ask where from you took these electrons, take into account that they do not work now as electrons. And this correction says how will decrease Drude.
but when you do like experimental measurements, what you measure is the conductivity due both to normal electrons and Cooper pairs.
Yes.
So
How to distinguish?
yes.
You can distinguish only by temperature dependencies. I mean that, of course, you measure all together. We will speak about this later, but I mean that questions which you can ask are, what is TC? How you define TC? Half of transition? Or where is maximal derivative? Or where resistance increased for 0.1 or 0.9? All this is voluntaristic. I propose you other scenarios. I do not know what is TC and you do not know. You give your experimental curves and we fit it with the full formula for conductivity, including all contributions. And then we propose you some TC. And I will show how it works. Okay, so now I want to recycle all this story. So I want to move from here to here, to quantum phase transition. So I want to move to study how quantum fluctuations. Here, fluctuations were some long waves of the order parameter, like in violin. But when you move along this line, here enter in play magnetic field. Magnetic field produce you, so each force Cooper pairs rotate. If the Larmor radio or magnetic length is very large, so forget about this. But at some moment, magnetic lengths will become comparable with Ginzburg Landau lengths. And at this moment, they start to do something with Cooper pair. What happens? I want to see it here in the limiting case. So here, temperature is 0. We speak about quantum fluctuations. I approach critical temperature, HC2 from above. Now I want to recycle this table in this one. How? I will start from a lifetime of quantum fluctuation. I will again say that it is h bar divided some energy. What energy? Here I use T minus TC. What I have to use here? Something which will turn 0 when I approach HC2. What energy is related with magnetic field? Larmor frequency. So I calculate Larmor frequency in my field H. minus this value at HC2. And this will be, if you put the values, you will find, you see that this is BCS gap multiplied reduced magnetic field. So I find the tau quantum fluctuations. Look, this is our old result with correct coefficient. Tc minus 1 divided T minus Tc over Tc. So reduced temperature. Here will be delta minus 1 divided reduced magnetic field. Delta minus 1 is Tc minus 1. This is the same, 176 difference. So actually, the only difference that here I had reduced temperature and here reduced magnetic field. And I can calculate also characteristic size of this fluctuation formation. It will be CBCS divided square root of reduced magnetic field. Now I want to understand what does it mean. Namely, I want to return to go for 1 step below and to see what happens. Below, in mean field, I have abricos of length. Cooper pairs rotate in vertices. The characteristic size is psi BCS size. And characteristic psi, the time, is period of rotation. Period of rotation is delta minus 1. So what I found is that the characteristic time of quantum fluctuation is much larger than period of rotation. And characteristic size of this something is much more than size of one vertex. So one Cooper pair which is formed in strong magnetic field, slightly above HC2, immediately starts to rotate. Period of its rotation is delta minus 1. But it has time to participate in many rotations. I have square root in the denominator. I have, sorry, not square root, I have small parameter denominator, 100. So 100. So, and size, which characterizes me all this, is not one vertex, but 10 vertices, square root of 100. So, what does it mean? This means, as I imagine, that if I would have camera and possibility to put exposition time 10 minus 11, I would see some piece of abricos vertex. And if 10 minus 9, I would see nothing, because all will be smeared out. Closer to HC2, larger these clusters, and longer they live. In HC2, abricos of lattice is formed and it becomes thin. So
Andrey,
yes,
the vortex phase diagram seems quite sensitive to pinning and other issues.
no, pinning still not, of course, but this is later. I mean,
This is late.
I just want, of course, you are right, but of course, you could tell me even without this that there is no here, that here there is no abricos vertex. There is a liquid.
Yeah, maybe.
But this liquid has the same character of melting, etc. So I speak here just so this image of clusters I match with this, not with so complicated. This is another story.
Okay.
Of course, I simplify to understand. And you understand, Mohit, that I calculated all propagators and diagrams in the regime of quantum fluctuation. These my fantasies are based on the exact answers. Moreover, we just now published a proposal for experimentalists how to measure this. It is not direct current. It is necessary to measure impedance because corrections to direct current are very slow, logarithmic. While for impedance, they will be the power singularities. Okay, so probably I finish. So my imagination now, the quality of imagination, what happens here, this is a phase diagram of superconductor. Here we know this is Meissner state. Here should be Abrikosov lattice, but we know that all is not so simple. Actually, there is a vertex liquid here, and I propose that here there is a Hc2 of temperature. This is a mirror field, and this mirror field magnetic length for Cooper pairs becomes comparable with Ginzburg-Landau. Here we will leave classic relay Ginzburg fluctuations. Here they start to be the vertices, these long wavelengths start to be distorted by magnetic field. Happens such formation of vertices, and finally I can describe here in the regime of quantum fluctuations as the formation of clusters of Abrikosov vertices, which then can be continuously pass to mean field application. Okay, so I finished the first part of my talk, and now I still have half an hour. Yes. So it will be much more simple. Yes, please.
Can you maybe say a bit more what is actually fluctuates in this quantum regime?
In this quantum regime, you have again Cooper pairs fluctuation, but they are not free. They must rotate.
So these are fractional vortices?
No, they are pro-image of. They rotate in two-dimensional case. They rotate like Cooper pair rotating vertex, but there is no long-range order. There are pieces. Sorry, there is no lattice.
So
But it grows, and finally, when you cross Hc2, they will pass to lattice. Then we will speak about the effect of pinning, etc. But the question is how they affect on physical properties. And this answer can be given. It was given first by Galitsky and Larkin in 2001 when they calculated contributions of this type of fluctuations close to Hc2 to conductivity and to the magnetic susceptibility. The answers were logarithmic. So it is not easy to measure logarithm of H minus Hc2. It is slow dependence. We propose to measure impedance. And our prediction that the corrections to impedance, so if you measure sigma of omega, so for clean superconductor, you should have a gap. So all story at zero temperature will start at 2 delta. If you are in magnetic field, the system changes. Nevertheless, so it was calculated by Maki once. Nevertheless, there is this gap. Our statement is that if you take into account these fluctuations, so your imaginary part in impedance will appear much before gap. It will be gap multiplied H minus Hc2 divided Hc2. Yes.
Would that mean that the imaginary part of the inductance diverges?
Yes. Yes. Okay, diverges up to some. This divergence we can cut. So in some range of magnetic field, not very close to Hc2, it diverges. Then it will actually match with results below Hc2. Of course, it diverges, and this is the essence that you can study this divergence and see. This is not logarithm. This is 1 over H minus Hc2. So much more visible. Now I wanted to be trivial, some deductive, just to for future, for next lecture. I want to prepare the ground, recording you. So a brief excursus on the Ginzburg-Landau phenomenological theory of superconductivity. So in 1937, a lot of people tried to explain superconductivity. I don't know how do you know the story, but for instance, Einstein proposed his theory of superconductivity. It was wrong. The same Camillin Boris, Kramers, Bohr, Landau in 1934 proposed wrong theory of superconductivity. That in each wrong theory there is something maybe reasonable. And Landau proposed in 1934 to expand free energy over superconducting power. It was wrong. But when you study, knowing this, you study his paper of 1937 of the phase the phase transition of the second order, you recognize that he already thought about this 3 years ago, and he proposed now to expand free energy over something which calls not superconducting current, but other parameter. Other parameter for the let's say for the binary alloys. This is a difference between the probability to occupy the site in lattice of the atom A or B. So this is scalar. For ferromagnetic-paramagnetic transition, this is magnetization, this is vector. For helium, this is complex wave function. For superconductivity, this is complex wave function. For helium-3, this is tensor. So he does not actually, he uses the only because then he choose the expansion over the only odd powers of other parameter. And here, the only point where he choose, he show the tensor nature of other parameter. He says that the even power should not be because even, yes, because
no, in the free energy it's even powers.
Yes, because no, for me odd and even. Sorry, but 50 years I do mistakes in English. What is odd? What is even? So
even second, fourth.
Yes. So over even over even powers, because he says that if we will take into account also odd, so for vector other parameter, I will change the frame and I will change the value of free energy, what is impossible. So this he constructed this beautiful classical theory of phase transitions of the second order. And I will just remind you that the idea was very simple, that if I will write the thermodynamical potential of free energy as expansion, so there is something which is other parameter, which changed me to phases. And he believed that above critical temperature, the free energy should have the shape of normal parabola. Below, force other parabola. So he assumed free energy in the expansion of this other parameter, even. And then the strong statement that the coefficient A changed its sign in the point of transition. So you pass from this parabola here, and you immediately have here always 0 for the parameter, so there is no magnetization. But so probability to occupy site in binary alloy is the same. And here there is a break of symmetry, a spontaneous break of symmetry. Very good. So then he introduced the reduced temperature. He defined that parameter A is alpha tau, where tau is the reduced temperature, it changed sign. And then he states that above TC, the average order parameter is 0, maybe fluctuation, but 0. And here you have two minima. Very good. It was 1937. In 1941 started the World War. Actually, it started in 1939. But the Russia, Soviet Union, and in the war in 41. And Academy of Science was evacuated from Moscow to Poland. And there, the positive effect, because Ginzburg was a young researcher, and he worked in Physical Institute of Academic Science. Landau worked in the Institute of Kapitsa. And these two institutes were not very friendly. the effect of this evacuation resulted that the scientists were mixed. And Ginzburg was interested very much in superconductivity. He was not satisfied by London theory. And he learned the Landau theory of second order phase transitions, and he came to Landau. He approached Landau. You understand, Landau was the great scientist, etc. Ginzburg was a young researcher. He approached Landau and proposed to extend the Landau theory of the phase transitions of second order to superconductivity. What problems were? First, you in principle, knowing about the existence of Meister effect, you could not believe that order parameter is a constant. Because it was evident that the critical current which expels magnetic field means that something happens. You cannot consider it as a constant. So first, the theory of second order phase transitions had to be extended to be non-homogeneous theory. So not on a scalar, it should be function. And then they recognized it as a complex function. The second, you could not consider superconductivity separately from magnetic. So you had to take into account the vector potential. So order parameter becomes function. So you have to write some the function and vector potential, and you have to make a piece between them and so for each point. So what was done? First, the Landau free energy or thermodynamic potential, which was function of order parameter, now was recycled as a function. So now free energy is a function of function. This is functional because order parameter now is a function of point. But where is magnetic field? There is no magnetic field. It is easy to add magnetic field just like the fact that when magnetic field is expelled, you lose h squared divided 8 pi per centimeter cube. So you lose magnetic field. Very good. So it was probably not difficult. But the great achievement of Ginzburg and Landau was that they wrote the theory in gauge invariant form. So they, from electrodynamics, from the field theory, they knew that momentum should be gauge invariant. So in presence of vector potential, from momentum P, you have to extract minus Q divided C or plus Q divided C multiplied vector potential. And here, what they did, they took into account this fact, recognizing that, look here, I forgot to say that their important achievement was that they do this expansion over even powers of order parameter, plus then say that the fact that order parameter change in space must be taken into account as expansion over also gradients, and again gradient square. The kinetic energy, it increases. I say always that Italy, as a patriot of Italian patriot, I say that Italy is a country of great gradients. You change, you go from one hill to another, 50 kilometers, and food will be another, wine will be another, pictures in museum will be another. And this is the richness of Italy, because this is a country of large gradients. So they added, before magnetic field, they added here gradient term. So they did expansion not only over order parameter powers, but also gradient. And then they recognized in this gradient, they recognize that in quantum mechanics gradient, this is operator of momentum. And if you have multiplied on E, H, and you will have momentum. So if this is momentum, please do it gauge and wave. So they put they added magnetic field here, and here in gradient term they added a magnetic field to make theory gauge invariant. By the way, BCS is not gauge invariant. And it was a lot of very productive discussions. Both knows perfectly paper of Anderson of 1958, which produced 2 Nobel Prizes of Landau, the Higgs
And Engle.
yes. Okay, so
Yes, that's one question. Isn't there a precursor of this relationship between the current and vector potential also there in London theory?
now you will see immediately. It's a very good question. I will reproduce immediately. You're right.
Andrey, I have one comment.
Yes.
Historically, they did not know the 2E. They wrote E star in Ginzburg and Landau.
Of course, absolutely, you're right.
This is history.
No, absolutely. 2E, it is for already modern treatment. As Abrikosov cheated us, telling that London's wrote their first equation, assuming that there are some electrons which do not interact with lattice. It was just convenient to say at the lecture, cheat students, because if you read London, by the way, he was in Poincaré Institute here guest because the money he immigrated from Germany, and he wrote London equations in being in Oxford. But then money finished, and he was a guest of Poincaré Institute. And here he published beautiful paper in Nature where he explained all physics of his equations. He explained that the fact that for him important was not superconductivity. For London, the starting point was the absolute diamagnetism. And he compared superconductor with diamagnetic atom. And he told, write wave function of electron. Impose magnetic field. You will have correction to wave function proportional to the square of magnetic field, evidently. And then calculate correction to current. And you will see that you will have response on vector potential. Not on magnetic field, but on vector potential. So it was super current. And it is why then he told that this very, very beautiful, I recommend to read it in Nature. And it is affiliated with Poincaré Institute. So better to read not first paper, which was a little bit, but the second where Fritz London explained it. Okay, so you are right. Now I will show how.
Yeah, and just one comment, because there is also a very nice review article by London in French. When he was at Poincaré Institute, there is a very nice review article by London in French. So which many people in the audience can read it.
Thank you.
It's a beautiful one.
Give me.
Give me
Yeah, thank you. Because I speak about short letter.
Yeah, it's beautiful one. So where you
actually, what is fantastic is that when Bardeen was receiving his second Nobel Prize for superconductivity, he expressed pretension for Nobel Committee that London did not get Nobel Prize. He told that the contribution of London to superconductivity was absolutely fundamental. And the notion of macroscopic quantum state was introduced by London. And London, by the way, 2 months later, after the discovery of superfluidity, again being in France, he proposed the explanation that this is Bose condensation of helium atoms. No one remembered about the paper of 1924, before quantum mechanics, of Bose and Einstein, because it was done just for identical particles. And it was before Pauli, etc. And London appealed to this paper and told about possible Bose condensation of atoms of helium. Then Tissa proposed to liquid model, but he was collaborator here of London. Okay, so now I will not go in detail. So we have function of free energy and what corresponds to the ground state of system. You have to calculate. You have the functional of two functions of order parameter and vector potential. Calculate two variational derivatives, and you will get the certain point of this. So first, okay, maybe I will not calculate the variation derivatives. I will recall you. Okay, one I will. So I calculate variation over psi conjugated. So you see that from psi square remained psi delta psi conjugated. Here I have psi modulo square psi delta psi, and unfortunately the problem is here. Here is okay, but so now I have to to extract this delta psi from nabla operators. So the little bit of mass, I just use the relation that the divergence of, okay, this is vector analysis, simple vector analysis, which I apply here. Finally, I will get, I will transform this integral to good one. Delta psi is out, yes, here, out of parentheses. And here I have some surface integral. And this surface integral must be 0, because I want to have 0 for any variation of conjugated function. So I will imply the boundary condition that this guy in the parentheses should be its product with normal vector must be 0. This is boundary condition. And after this, I get the first Ginzburg-Landau equation. So you see that this is nonlinear term, unique term, and this is the equation which corresponds to the variation over other parameter. Then the story can be repeated. Variation, we can calculate variation derivative over vector potential, and it will give me the equation for vector potential. It will be double curl equal for PGS, and GS, look, GS, this is the usual expression for quantum mechanical flow probability minus the response on vector potential. And now I return to your question. I will say that in the homogeneous case, so Landau equations, when psi is constant, these terms disappear, and I will have the GS is proportional. GS is proportional to vector potential, which we understand calculate time derivative. It will be dg over dt equal electric. So this is the hypothesis of Brothers-Landau. So and I immediately said this Ginzburg-Landau equation is reduced to first London equation. Very good. So now I still have 5 minutes and finishing. Okay. So okay. So I demonstrated how to get first London equation and second London equation. This is trivial for constant. So I compare the square of other parameter with the superfluid density, and they produce the penetration depth. Okay, achievements of Ginzburg-Landau. First, very important achievement that they have succeeded in the calculate the energy at the NS interface. So they demonstrated that if the Ginzburg-Landau equations can be written in the form dimensionless, and they demonstrated that there are two lengths of one parameter, the ratio of this length, so-called Ginzburg-Landau parameter. This is a penetration length and size of Cooper-Perry psi. And for those old superconductors, the penetration length was always much less than size of Cooper pairs, even with 10,000 angstroms. And in this case, they always got that the energy is positive. So to create interfaces between superconductor and normal phase cost money, cost energy. And it justified the existence of intermediate state postulated by the Payens, Landau. So this was justification of the scenario of coexistence of magnetic field and superconductivity. But when they calculate this sigma Sn as a difference between normal free energy and superconductor, they found some unpleasant, that it can be negative. But for superconductors with very short small pairs. And they thought this does not exist. Then Ginzburg-Landau theory permitted to calculate critical current and critical field in confined superconductors. So for films, magnetic field depends on parallel field, and wires. I do not have time to stop in this, and this is not my work. Then, what is very important, that Zavaritsky in 1952, experimentalist in Landau Institute, was supposed that he will check the results of Ginzburg-Landau theory experimentally. He found great agreement, but his boss, Shainikov, told, no, you cheat us, because you grow the films at room temperature and measure at helium. No, grow at helium, do not heat it, measure, and then do what you want. And they found contradictions with Ginzburg-Landau theory. Abrikosov was proposed to explain this. He started in 1952, and in result in 1954, we here already solved Ginzburg-Landau equations in assumption that kappa is more than 1 over square root, which Ginzburg-Landau denied. And he found completely different solution. He found that magnetic field can penetrate in superconductor in the form of vertex of normal phase, not intermediate state, by mixed state. And here, the fractionalization of phases is sigma is negative. More interfaces you will produce better. But how you can fractionalize it? Up to one flux of magnetic field. You cannot have less. And this stopped the story. And Abrikosov found this lattice. And Landau did not allow him to publish this. Until in 1956, Feynman did not publish the theory of rotating helium. When he demonstrated, it was another story, how helium, superfluid helium can rotate. And he demonstrated that, and Landau did mistake also there, because he believed that it will be something like intermediate state. So while layer, normal, one superfluid, one normal, one superfluid. And Feynman demonstrated, no, it appears first vertex. And when this article arrived to Moscow, Landau told, oh, we were stupid with Lipschitz. This Feynman is great. In this moment, Abrikosov approached him, told Landau, you say that Feynman is great with one vertex. I proposed you 3 years ago the whole lattice, and you told me that I'm idiot. So finally, he published this article in 1957, which gave him after 50 years Nobel Prize. Okay, so I will show you. So this is the facsimile of Abrikosov presentation slide about the superconductivity. And Here you see the direct observation of individual flux lines in type 2 superconductors in 1967. Then here, trivial statements that high critical currents are important, but this already necessary to speak as Mohit, of course, about pinning, etc. This is not my field, but I want to show you that indeed, Mohit, I answer to you now. This, look what are doing people from our ex-alma mater. This Andreas Glatz and his company solve the time-dependent Ginzburg-Landau equation with so this is superconducting film with dysprosium. So IPCO with dysprosium, terrible, but I will show you. So what they did, they measured distribution with a scanning tunnel and electron microscope. They measured distribution of these clusters of dysprosium. Then they do three-dimensional tomogram, reconstructed landscape, simulated vertex dynamics, and you see what happens now. I will show you how to do this. This is a supercritical current. So vertices you see from above, red balls, these are dysprosium clusters, and they pinned some vertices, but some of them, because current is too high, so they move. And all this is obtained from Ginzburg and Landau equation. So I think that Ginzburg and Landau should not sleep well in their coffins. Nobody will what happens after the 75 years with their equations. Okay, thank you very much for your patience. I continue.
Questions?
I have a historical question.
Yes.
How come he couldn't publish? What was the standing of Landau that he could prevent Abrikosov from publishing a paper? He was his like direct.
You are son of democratic society. Because when you signed, this is other story. This is other story and comment. But I won't say that. I suppose that in France, because what the procedure was in Soviet Union, especially in Landau Institute, where was absolutely the dictatorship. So you was supposed, if you did pay, you have to present your paper in the presence of all institute. Every Friday, it was, okay, in those times, it was only Landau group in Kapitsa Institute. In my times, all members every Friday in Chernogolovka, all in more or less like this lecture hall was full. Then people, I only did my master in Landau Institute. So actually, I'm not patriot of Landau Institute. I recognize that it was a lot of players of great scientists, but the atmosphere was, I will tell you truth, that mainly up to my mind, people asked not to learn truth, but to demonstrate that they are more intelligent than the speaker. This is a style which followed from Landau. So you should pass the improvement of personnel Landau those times. If not, you cannot publish, you cannot put your name with affiliation of Landau Institute. And it was until the light, it is now being in Argonne National Laboratory, we did not even have an Abrikosov as a group leader. Mohit, we did not ask him permission to publish. Not. You are the staff of Argonne National Laboratory, and you already is approved to put affiliation. The same in France, the same in Italy. In Soviet Union, it was not so. I don't speak about that then you had to pass the so-called first department, so KGB. Yeah. You have to declare that your article does not contain nothing, does not contain anything which was to be published. So, because if not, it would be immediately put the secret. So, and you could not publish. So it is Landau just told, no, it is shit. You will not publish. No, this story I know personally from Andrey.
So may I make another comment here on
Yes.
the history? But Abrikosov, who didn't necessarily have very kind words for many people, nevertheless, absolutely did not bear a grudge against Landau for having prevented it. Even years later, he would say,
You're absolutely right. Abrikosov was famous for his. Abrikosov was famous by his words. Once he was asked, "Dear Alex, Alexei Alexeyevich, what do you think about academician folk?" Abrikosov thought a little bit and told, "Unfortunately, about Vladimir Alexandrovich Fogg, I cannot say anything bad." It was his famous talk. So you are right when he spoke. Nevertheless, about Landau, but you see, it was an incredible discipline that Cora Landau, the wife of Landau, wrote her memoirs. In such 2 volumes, typewriting in 6 copies. And she gave one to Abrikosov, one to Kapitsa, one to Pitaevsky, one to Gorko, one to Zeloshinsky, and one to her son. After 1 week, Kapitsa read it, collected all, and told immediately burn. Abrikosov, of course, didn't. And Abrikosov told me all this story. And when he died, his widow brought, she was our guest, and she came to Italy, and she brought me this. I have these 2 volumes in original. And then we went to Pitaevsky to visit Pitaevsky because she wanted to see Pitaevsky. And after lunch, we spoke. Pitaevsky was 87. He was academician. He was professor already 30 years, Italian professor of Chiara Fama, etc., etc., famous person. So, and she told, Lev, by the way, I brought the memories of Cora Landau to Andrey. Pitaevsky looked at me and told, Andrey, do you have this manuscript? I told, yes. He told, immediately. I asked him why. Kapitsa. I told him, but Lev Petrovich, Kapitsa was authority for you, not for me. I will leave this document to the Italian Academy of Science and Letters. I already promised. So you cannot understand this generation. Okay, if there are some other questions.
Okay, so we thank Andrey again.